This is video 10-1, Kinetic Molecular Theory, Properties of Gases, and Deviations from Ideal Gas Behavior. Chapter 10, Physical Characteristics of Gases. Okay, so first thing we'll look at, something called the Kinetic Molecular Theory. This applies not only to gases, but to all states of matter. So, this is based on the idea that particles of matter are always in motion. An ideal gas is a gas that perfectly fits all the assumptions of the kinetic molecular theory, and we'll go over what these ideas are in a second. Okay. Now, one problem with the ideal gas, it does not exist. Okay. So, with respect to gases, what are the properties of gases in terms of the kinetic molecular theory? Okay. First of all, gases exist of large numbers of tiny particles that are far apart relative to their size. And don't forget, the particles are really small. So, even though the distance between the particles can be really, really small, they still seem like they're pretty far apart. Okay. Now, when the particles collide, they collide with other particles and they collide with the containers, the sides of the walls of the containers. These are known as elastic collisions. In other words, when they collide, none of the energy gets changed into heat. All of it is just going to be kinetic energy. Okay. Particles are going to be in continuous, random, and rapid motion. Particles will always travel in a straight line until they hit another particle. Then that particle will bounce off in one direction. This will bounce off in another direction. But this particle will continuously travel in a straight line until it hits another particle. Then it moves off in a different direction. Okay. And there's no attractive or repulsive forces that exist between the particles. Now, this is a reason why ideal gases do not exist, because in real gas particles, you have to have attractive and or repulsive forces between the particles. Okay. Now, the average kinetic energy is energy in motion, of the gas particles is directly proportional to the temperature of the gas particles. So, in other words, as temperature increases, the kinetic energy of the particles will increase and the particles move faster. Okay. Now, kinetic energy, this formula is equal to kinetic energy of anything that's moving is equal to 1/2 times mv squared. Okay. The particles of all substances at the same temperature have the same average kinetic energy. So, as long as the temperature of object 1 is the same as the temperature of object 2, which is the same as the temperature of object 3, the average kinetic energy of all the particles is always going to be exactly the same. So, anything at 25 degrees Celsius, all the particles, no matter what type of substance it is, every particle will have the same average kinetic energy. Okay. Now, properties of gases. Gases, as you know, can expand. Okay. They have no definite shape or volume. They're always going to fill up the container in which you put them in. And if it's an open container, it's going to fill up the container plus expand as big as possible. Okay. Fluidity. Gases are fluids. They will flow. So not just liquids can flow, but also gases. They have a low density. Okay. About 1/1000th the density of their liquid state in general. Compressibility, you know, you can take a gas because you have all this space between the particles, you can force them closer together. Okay. Because in real gases you do have attractive forces, sometimes you can get condensation taking place. So the gas turns into the liquid state as a result because you do have attractive forces. Now, you can't just take a gas and compress it and say, oh, it's going to turn into liquid. It depends on what temperature it's at and what pressure it's at also. Okay. Diffusion. This is defined as a spontaneous mixing of gases. They will always move from a higher concentration to a lower concentration. Okay. So if you open a bottle of perfume, when you stand next to it, it smells really strong because it's going from a high concentration inside the bottle of perfume. The gas molecules in here, highly concentrated, and then they will start spreading out more and more and more, okay, until you get an even distribution. And how fast diffusion occurs depends on the speed of the particles, the diameter of the particles, any attractive forces that exist between the particles. Okay, now one problem with diffusion. Open this perfume bottle and you can time how long it takes to diffuse through a room. Do it again with the exact same sample, exact same room. The diffusion time may or may not be exactly the same because of the speed can differ. The collisions, as this particle collides, is it going to always collide in the exact same time, the exact same way that it collided the first time? So diffusion will not always be exactly the same every time you open this. Okay. So what we use instead is something called effusion. Okay. And basically gas particles move through the tiny opening. So if you were to take an aerosol can, okay, and you have a tiny opening there. So now when you push down on this, gas comes out through the opening. This is known as effusion. Okay, and it depends on the velocity of the particles. Okay, now, deviations of real gases from ideal gas behavior. Okay, real gases are the gases that actually exist. Ideal gases are the ones that don't actually exist. Okay, so many gases, why do we study ideal gases? Because a lot of real gases can behave like ideal gases. Okay, now, what's the difference between a real gas and an ideal gas? Okay, an ideal gas and a real gas. Okay, one is in terms of the particles. In an ideal gas, the particles in an ideal gas have no volume. In a real gas, the particles themselves do have volume. Okay, and in an ideal gas, there's no attractive forces. So if you take an ideal gas and you squeeze it and put it under lots and lots of pressure, the gas will always get smaller and smaller and smaller. You could keep condensing the gas, compressing the gas indefinitely. In a real gas, because the particles do have volume, at some point the gas particles will actually start touching each other, and at that point you couldn't compress any smaller. Okay? In an ideal gas, there's no attractive forces. You cause the particles to get closer and closer together, they're not going to change phase. In a real gas, you do have attractive forces. So at some point, the gas will actually turn into a liquid, and it's not going to be any more gas loss. So how do we make a real gas behave like an ideal gas? These two conditions. High temperatures. Okay? High temperatures basically compensate for the attractive forces. If their particles are moving fast, the attractive forces won't take place. And also low pressures. If you have a low pressure, the particles are far apart, and the effect of the volume of the molecules in a real gas is negligible. Okay, and when are they going to deviate greatly from ideal gas behavior? In other words, when aren't they going to act like an ideal gas? Pretty much the opposite. If it's low temperatures, the particles are moving slow and the attractive forces can start taking place and cause condensation. And if it's high pressures, then the particles are really close together, and all of a sudden the volume of each individual particle in the real gas does start to take effect. And here's the review question. Can water vapor behave like an ideal gas?